Hello, everyone. I'm Ryan.
I'm Ajay.
I'm Satya.
I'm Vivek.
I'm Hamza, and today we'll be predicting NBA wins.
So I'd like to give you guys a brief introduction to the NBA. There are 30 NBA teams, and each NBA game consists of various statistical measures, such as points, rebounds, and assists. And our goal in this project is to predict whether an NBA team will have an above 500 record. This basically means if the team will win more than half of its games. So this will be a binary classification problem with a 1 signifying the team will have an above 500 record and a 0 signifying otherwise. So the data we collected is from the following website, basketballreference.com, and we have 3 data sets from the following years of 2019 all the way to 2022. And the first 2 years will be our training data, and the last year will be our testing data. So each data set consists of 30 rows, which represent the 30 NBA teams, and there are also 50 columns. These columns consist of both offensive and defensive stats, and the last column is our target column, which is titled one more than half. And a 1 signifies the team has an above 500 record, and a 0 signifies a 500 record or lower.
Before we could use our data sets, we had to clean the raw data to make sure that it didn't mess up our classifiers. So we would go in and we remove and fill in the data whenever required. The training data sets were merged together first and foremost, columns with strings or either dropped or replaced with numerical values whenever possible. Furthermore, missing values within the columns were replaced with column means. After pre-processing, the data ran successfully through the various classifiers.
Before we get into the exploratory analysis and feature engineering phases, here are some of the common per game features so that they don't come as a surprise later. Note that these features are divided into two groups, offense and defense, because the NBA datasets are divided into team stats and opposing stats. Let's get into the exploratory analysis phase. During this phase, we first train the basic CatBoost model on the datasets without any modifications. This will serve as a base reference for the created datasets later. Because CatBoost is a robust model, it actually did pretty well and achieved high scores on the testing data. And by extracting the most important features used for training, we learned that the model really favors defensive stats. The top three stats, points, three-pointer percentage, and field goal percentage, are all defense stats, and they're at least 2 times more important than all other stats. Although it's intuitive to see point-related stats be the most important, the model suggests that teams with great performance on defense are most likely to win. We'll see a similar trope for later datasets. For the feature engineering phase, we created new datasets from analyzing correlations and noting data types. For the first dataset, named transform teams, the team name feature had many unique strings, making it hard for the model to train on. Since the teams were divided into Eastern and Western conferences according to the NBA season summaries, we replaced the team names with the Eastern Conference feature and mapped the teams accordingly. For the ratios and counts-only datasets, we noted that we had features that represented the same information. For example, field goal percentage encapsulates field goals made and field goals attempted. So we created datasets that preserved only the ratios, like field goal percentage, or only the counts, like field goals made and attempted. Lastly, since we noted that each feature had offense and defense counterparts, we created datasets where the offense and defense stats were averaged. The feature importances of the transform teams, ratios only, and counts only datasets are shown in the figures on the left, center, and right respectively. And the performance of the basic model on each dataset is shown in the table below. Although none of the datasets caused the model to perform better than the original, the transform teams and ratios only datasets were on par. This may be because the original model heavily favored the points, three-pointer percentage, and field goal percentage defensive features when training. And these features were preserved in these datasets. However, the counts-only dataset performed a little bit worse. One reason for this is that the model really liked the ratio features, So removing those features meant that the model had to rely on other not so good features. The overall results suggest that the model doesn't need the count features and instead can do just as well with the percentages to make predictions. Upon looking at the average data sets, we saw poor performance. One reason for the poor results is that the correlation between the offense and defense features were fairly low, suggesting a significant difference between the two types. Thus, averaging the two types resulted in meaningful information loss. Needless to say, we didn't continue using these datasets for training other models. However, the datasets previously seen all had good results, so we passed those sets to the model selection and hyperparameter tuning phases.
So this is the correlation heat map of our various features, including the target column, and we can see that the percentage features actually have a much higher correlation with our target column. So for some of our models, we trained them specifically on the data sets that include these percentages. The first model we used was the XGBoost model, and it performed the best on the ratios only data set and with an accuracy of 80%. And hypertuning was done with the N estimators, and it really didn't cause that much improvement on the model. Our next model was logistic regression, and it had a base score that performed the best on the ratios data set with an accuracy of 93.33% and an AUC of 9.9305. Hypertuning was done with GridSearch CV, and the best score acquired was 9.98763. However, in general, tuning actually reduced the accuracy of the logistic regression, so we ran with the base model for our predictions.
The next classifier that we use is the CapBoost model, also on the trained ratios dataset. So the base CapBoost gave an accuracy score of 83.3%. We tried tuning the following hyperparameters you see on the screen. However, this does not improve the accuracy. For example, the accuracy after tuning was either the same or lower than 83.3%.
The next model that we tuned was the random forest model. So the base random forest model managed to achieve a 77.4% accuracy on the 2021 and 2022 test data. After tuning the hyperparameters, as you can see on the screen, the accuracy managed to increase to 80.6%. And this was the tuning machine we used for the random forest. Further feature selection was done on the random forest to attempt to increase its score. Through the use of sequential feature selection, ideal features were selected from the dataset. These ideal features were combined into their own dataset that random forest was trained and run on. After this second feature selection, the accuracy of the tuned random forest increased to 83.9%, which was the highest we could achieve with it. This was the feature selection that was done, so it would go through all the different features and it would select the specific features that had the most impact on the random forest. And it would tell us which features didn't, in which we would drop it to see if it would increase the score. As you can see below, those are the features we selected. The base model for gradient, the next machine we used was the gradient boosting machine. The base model for the gradient boosting machine managed to score a 74.2% accuracy on the 2021-2022 test data. After tuning the hyperparameters, gradient boosting was able to also score an 80.6% accuracy on the data. And the hyperparameters that were tuned were the ones that you could see on screen. And this was, again, the machine used to tune the gradient boosting.
So next we tried to use light gradient boosting. So without tuning, light gradient boosting yielded an 87% accuracy, but with tuning, it yielded 90.3% accuracy. N estimators was the only hyperparameter tuning that mattered and worked. So in conclusion, we had three key findings. Number one is the most accurate classifier. It was logistic regression. Feature engineering is effective for both random forest and logistic regression, and defense wins championships in basketball. In the future, what we want to work on is that we want to add data from more years. prior to the COVID-19 pandemic, basketball rules were a lot more different than they are today. Now, our 2019 and 2020 data comes from the COVID-19 pandemic, and that data is a little bit skewed since there were less games that were played. Adding more data from years previous would help minimize the effects that the skewed data causes. Now, we also want to apply our data to the current season. Our findings and estimators, we want to see what happens if we can predict game results that are happening right now in this season.